This is Chapter 10, Section 4, Using Equilibrium Constants. We learned in the last section that any reversible reaction can be characterized by an equilibrium constant, and that the equilibrium constant expresses the relationship between the various concentrations of the different substances involved in the reaction at equilibrium. In this section, we're going to learn how Kc can tell us more about the composition of this equilibrium mixture, both qualitatively and quantitatively. The first thing to remember is this general form for the equilibrium constant. Kc, the equilibrium constant, is really a fraction or a ratio where the amount or concentration of the product is placed on top in the numerator and the amount or concentration of reactant is placed on the bottom or the denominator. Given that this is a ratio between these two quantities, if Kc is greater than 1, what that means is that the amount of products is greater than the amount of reactants at equilibrium. If Kc is less than 1, then the amount of products is less than the amount of reactants at equilibrium. To take this a little bit further, the size of Kc is actually telling us how far the reaction goes to the right. In other words, it's telling us how much of the reactants on the left-hand side have been converted into products on the right-hand side. If Kc is large, then that means that the reaction lies very far to the right, meaning that there are more products than reactants once this reaches equilibrium. So for example, if you react sulfur dioxide, SO2, with oxygen, O2, these can combine together to form sulfur trioxide. But of course this is a reversible reaction, like all equilibrium reactions are, so the sulfur trioxide can break apart to reform sulfur dioxide and oxygen. So if you combine a mixture of these chemicals into a closed system and you let it reach equilibrium, what you'll find is that because the Kc value for this reaction is very large, it's much greater than 1, you'll find that there's much more sulfur trioxide at equilibrium. These pictures illustrate this using bar graphs for the concentrations. So we can see here on the left-hand side, initially we have relatively large amounts of sulfur dioxide and oxygen, the two reactants in this equilibrium equation. The fact that Kc is large tells us that over time, most of those reactants will be used up and converted into the product sulfur trioxide. So at equilibrium, you can see we have very little sulfur dioxide and oxygen left, and much more of the product that's been formed. Again, the product is on top and the reactants are on bottom, so a larger number on top and a smaller number on bottom gives you a large value for the equilibrium constant, Kc. In this case, we say that the equilibrium reaction favors the product side. On the other hand, for reactions with a small value for Kc, they don't proceed very far to the right at all. This means that most of the reactants are not converted into products, and you have mainly reactants left at equilibrium. So for example, nitrogen gas, N2, can combine with oxygen gas, O2, to produce nitrogen monoxide in a reversible chemical equation. However, the Kc for this equation is extremely small. This means that if you combine nitrogen and oxygen in a sealed container at equilibrium, it'll still be mostly separate nitrogen and oxygen molecules with only very, very little converted into nitrogen monoxide. This is pretty important because our atmosphere is mostly nitrogen and oxygen. So if this Kc value were much larger than 1, then all of the oxygen in the atmosphere would be used up to convert into nitrogen monoxide, and there wouldn't really be any left for us to breathe. This illustrates the points using these bar graphs again. So at the beginning, we initially have a large amount of nitrogen gas and oxygen gas. And over time, after the system reaches equilibrium, only a little bit of the nitrogen and oxygen have been used up, and we still have a large amount of both. The little bit that's been used up has been converted into nitrogen monoxide, but not very much nitrogen monoxide. Again, this is because the Kc value is small, so the amount of product at equilibrium is small, the numerator is small, and the denominator, or the amount of reactants, is large at equilibrium. For a reaction like this, we say that it favors the reactant side. So if we think about how Kc is calculated and how it relates to whether a reaction proceeds to the right or doesn't, then we can get a sense of the range of values that Kc can take on. The first thing to understand is that since Kc is always calculated from concentrations, it's always going to be a positive value. It doesn't make sense to have a negative Kc value any more than it makes sense to have a negative concentration. It just doesn't happen. So the smallest possible value for Kc is actually 0. And since Kc is a ratio, for Kc to be equal to 0 must mean that the numerator equals 0, which means that the concentration of products must be equal to 0. So if an equilibrium reaction produces no products or 0 products, it means that the reaction didn't actually occur. Okay? So the lowest possible value for Kc of 0 really refers to the situation where there's no reaction going on at all. No product is formed whatsoever. On the other hand, we have large values of Kc. And large values of Kc can go all the way up to theoretically infinity. The way that this would happen would be for you to have some amount of product formed, but no reactant left over. Right? Since Kc is products over reactants, if you have some finite amount of product and 0 reactant, then what you would end up with is a number that tends towards infinity. In practice, this is usually just seen as a very large number or arbitrarily large or something like that. But what this means is that there are no reactants left over, and so the reaction has gone all the way to the right side. We can say that the reaction has gone to completion. So in another sense, these are not equilibrium reactions either. These are reactions that go from the left all the way to the right. So a true equilibrium reaction is where the Kc is somewhere in between this range. It has not a 0 value and not an arbitrarily large value, but it has some moderate value. If it's a small value for Kc, meaning less than 1, then there's mostly reactant and a little bit of product formed. If there's a large value for Kc, it means there's mostly product and very little reactant left. If Kc is approximately 1, then you have approximately equal amounts of both. Now, there are other considerations because we're using different substances. It's not just a direct ratio of one thing to another. There are sometimes several different substances involved and sometimes raised to a power and things like that. So these are just general guidelines, right? It's not that it has to be exactly 1 for the amount of reactants to equal products, but in that range you get an equilibrium with approximately equal amounts of both. One more thing to note is that the size of the equilibrium constant has no bearing on how fast equilibrium is reached. The rate of a reaction tells you how fast equilibrium is reached, or can be used to figure out how fast equilibrium is reached, but Kc itself doesn't tell you that. This chart shows you some examples of how you can use the Kc value to predict the equilibrium composition of several different equilibrium reactions. So we're still not at the stage of using this quantitatively yet, but we want to think about qualitatively what the composition of the equilibrium mixture will look like. In other words, is it mostly product, is it mostly reactant, or is it some combination of both in roughly equal amounts? The way that you can do this is, again, what we've been saying. Large Kc means mostly product, small Kc means mostly reactant, Kc of approximately 1 means roughly equal amounts of both. So for these first 3 examples, you have very large values for Kc. 2 times 10 to the 11th, 1.1 times 10 to the 7th, and 1.6 times 10 squared are all much larger than 1. And so all of these reactions are mostly product at equilibrium. For the next 2, they have very small reaction equilibrium constants, 1.2 times 10 to the minus 2, and 2 times 10 to the minus 9th, which means very little of these have converted into products, and so you have mostly reactants left at equilibrium. Here are 2 more examples. In the first equation, you have hydrogen gas combining with fluorine gas to produce hydrogen fluoride gas, and the equilibrium constant for this reaction is 1 times 10 to the 95th. This is an extremely large number, much, much bigger than 1, and so what this means is that this reaction does proceed mostly to the right, and so at equilibrium you'll have mostly products, mostly molecules of hydrogen fluoride with very little of the separate gases left over. For the second reaction, you have oxygen gas converting directly into ozone, O3. But the equilibrium constant for this is very small. It's 10 to the minus 7th, 1.8 times 10 to the minus 7th. And so what this means is that very little oxygen actually converts into ozone under typical conditions. This again is good because we don't want all of the oxygen in the atmosphere to convert spontaneously into ozone. We can't breathe or process ozone the same way. So for the first one, Kc is large, and we say the products are favored at equilibrium. For the second one, Kc is small, and so we say the reactants are favored at equilibrium. But now we can also use the equilibrium constant to perform some quantitative calculations. If we're given the equilibrium constant and the concentrations of most of the substances in an equation, then we can calculate the concentration of the remaining substance at equilibrium. So for example, here we have a reaction between carbon dioxide, CO2, and hydrogen gas, H2, and these combine together to form carbon monoxide and water vapor. If this reaction is run and left to reach equilibrium, and you come back later and you find that carbon dioxide is 0.25 molar concentration, hydrogen gas has a 0.80 molar concentration, and the water vapor has a 0.50 molar concentration, then you can calculate the molar concentration of CO, which is what this question is asking for. The way that you do this is by writing the correct equilibrium expression for the problem and then plugging in these concentrations along with the value for Kc. So the best thing to do is to write down all the information that you're given, including the Kc value, which is often given next to the equation like this. Figure out what it is that you actually need to calculate, and then you understand that you have to use the equilibrium expression in order to get from what you're given to what you need. So the first step is to write the equilibrium expression. In this case, Kc equals the concentrations of the products, CO and H2O, multiplied together. There's no coefficients in front of either of them, so there's no exponents needed. And those product concentrations are divided by the reactant concentrations for CO2 and H2. And again, there are no coefficients, or the coefficient is 1, so there's no power, or you raise them each to the power of 1, which doesn't matter. So this is the complete equilibrium expression for this reaction. This shows us what concentrations go in and where the Kc is. The thing that we need to calculate is the concentration of CO. And so we can solve this equation to get CO by itself, and we find that the concentration of CO is going to be equal to Kc times the concentration of CO2 times the concentration of hydrogen divided by the concentration of water vapor. Now that we have this expression, we can just put in the numbers. We can see that the concentration for CO2 is given to us as 0.25, so that goes here. The concentration of H2 is given to us as 0.80, so that goes here. The concentration of water vapor, H2O, is given to us as 0.50, and so that goes here. And then up front, we have the value for Kc, finally, which is 0.11. So 0.11 times 0.25 times 0.8, all divided by 0.5, gives us an equilibrium concentration for carbon monoxide of 0.044 molar. Now notice that the unit for the concentration is molarity, moles per liter. The units, as we said, don't quite always work out, or they don't look like they'll work out, and we're not going to deal with the more advanced treatment to make them work out. But just keep in mind that anytime you calculate a concentration from an equilibrium constant, the unit is always going to be capital M, or molarity. So here we have another example. In this case, phosphorus pentachloride is decomposing into phosphorus trichloride and chlorine gas, Cl2, and the equilibrium constant for this is given as 4.2 times 10 to the minus 2. They also give us the concentrations of phosphorus trichloride and chlorine gas. So again, the first thing we need to do is to recognize the concentrations that we're given and the equilibrium constant that we're given, figure out what concentration we're really looking for, and then we're going to need to write the equilibrium expression to connect the two together. So starting out by writing the equilibrium expression, we have the products on top, phosphorus trichloride and chlorine gas, both on top, multiplied together. No exponent because there's no coefficients. And then in the denominator, we have the reactant, phosphorus pentachloride, PCl5. Again, no coefficient, so no exponent is needed. We're looking for the concentration of PCl5 in this question. And for a lot of these equilibrium questions, you really need to be careful because the formulas on the left side and the right side can often be very similar, right? So don't confuse PCl5 with PCl3. We're looking for PCl5, and so we need to solve for that. So we can solve it to get this expression here. After that, it's just a matter of plugging in the answers. We know that the concentrations of both of the products are 0.10, so that goes into both products. And then we're dividing that by the equilibrium constant, 4.2 times 10 to the minus 2. Again, you should be practicing putting scientific notation into algebraic calculations like this in your calculator. But in a case like this, you could also just recognize that 4.2 times 10 to the minus 2 is really just 0.042. That might make it easier for you to enter. Either way, when you calculate it, you're going to find that the concentration of PCl5 at equilibrium is 0.24 molar. Again, don't worry about the units. Just remember that if you're calculating concentration, it's going to be molar units at the end.